In the next subsection, I want to talk about Quicksort. It's fair to say that that's my favorite sorting algorithm. I've worked a lot personally on researching Quicksort. I may actually be the person with the most papers on Quicksort, and well, I've worked a lot on this, so I have to keep myself to keeping the presentation here short. I have a lot more to say about this beautiful algorithm, but in the interest of time and for your sanity, I'll not do it. I asked you on Slido what is the main principle behind Quicksort, and let's briefly switch there. So there's 20 people who have voted. I'll give you a few more seconds to make up your mind. But I guess many will have seen this. All right, so there's a few don't knows, and we'll definitely have to change that. And a couple of votes for the other things, but the vast majority has the right idea in mind. I should say that this split elements around the pivot element would be, I think, a more appropriate way to phrase it. Okay, thanks for voting, and then we can continue. So yes, indeed, the essence of Quicksort is to take an element, to compare this with the other elements and split them into the smaller. I have to move over here. Split them into the smaller and bigger elements, and recursively sort these two. There's a bit of the you can do the details of this procedure in a better or worse way, and I'll show you one of the better ways. So again, pictographically, what Quicksort does is called partitioning. And I'll show it like this. So you have a completely unsorted list. There it can go arbitrarily up and down. After partitioning, there is a pivot point here where if you're on the left, you're below the dashed line, and if you're on the right, you're above the dashed line. That's the idea of partitioning. How can you do this? So here's your unsorted list, arbitrarily up and down. You nominate one element as the pivot element, and in this case, I just took the first one. No magic behind this. And then we start a process where we have two pointers that scan the array, one from the left and one from the right. And we will compare elements with this pivot. So this is indicated with these arrows below the elements. That's where we currently look at. This first element is smaller than the pivot, and it's on the left side. Remember, our goal is to produce something like this. So for the moment, this element is where it's supposed to be. It's on the left side of, well, wherever the boundary will be. But that one's good, so we can keep it where it is. And we move on to the next element. This is a bigger one. It's bigger than the pivot. So it has to go to the right side. We don't know where the right side is at the moment, but that's now the key trick here. We just remember that it's on the wrong side. And now we start a process from the other end and look what elements we find there. The first one is big, which means it's on the right side. And so we just leave it where it is. But the next element is smaller than the pivot. So these two now, we have a pair of elements that are both in the wrong order. Why don't we just swap the two? And with one swap, we get both elements on the right side, on the side that they belong. That's what makes this partitioning method efficient. You get two things done in one step. Okay, let's look how this continues. You find some more, and then one last pair that's out of order. And now at this step, you notice that these two pointers that started at opposite ends, they have crossed. They have reached a common point. And that's your signal that you're actually done. Now, the only thing that remains is to put your pivot element in the middle. And then you have exactly this picture from here. There's the dashed line, right? It's just given by the pivot element itself. And we return this position. That's another important part of partitioning. Because, I mean, here, this is almost in the middle, but we don't have a guarantee. It could be slightly more to the left, slightly more to the right. That's not something we know up front. Okay, a few remarks. We don't need extra space. This is all inside the original array. We only swap elements around. We don't have to copy them into a buffer space like in merge sort. We visit every element exactly once. We kept the pointer on one of the left side occasionally and had to wait till some partner was found on the right side. But that pointer still, it just stays there. So we count that as one visit, which makes sense in terms of memory accesses. Again, I have more to say on this, but not here, not now. Ask me offline if you're interested. And the last point, what I already said, we return, as the return value from the partitioning procedure, we return the position of the pivot at the end. Good. With that preparation, we can give the detailed code for Quicksort. Now, it's not ideal. This is the partitioning procedure that describes precisely what I've just shown you in this example. Now, I'm not claiming there's any rocket science going on, but it turns out that this partitioning procedure is very easy to break and get wrong. So if you ever have to implement this yourself and cannot use a library implementation, consider using precisely this code, because that's the one that the Quicksort expert recommends. And that's not just me, it's also Robert Sedgwick is the other Quicksort expert, and he's worked on this code as well. That's the one that avoids all the known pitfalls and just works as given. Apart from that, I don't want to comment more on the code. It's doing exactly what I showed in the example. There's a pointer I starting on the left, there's a pointer j starting on the right, and then they move towards each other one step at a time, as long as you're smaller than this pivot element, which is always in the first position here. One comment here is you can pass the partitioning method a position that you want it to use for the pivot element. And then we just swap that to the first position. Yeah, and this picture below that I'm hiding here is the invariant that holds during the execution. There's the part on the left of I that's small, the part on the right of j that's big. The part between them is unknown as of yet, and the pivot is in the first position. There was a question on Slido. This is an interesting remark. Let me flag the question. So it's true that you can very easily write very short code in functional programming languages for methods like Quicksort. I think the same is true, maybe not 3 lines. Oh, you changed it to 4 lines. I think the same is true for merge sort pretty much. I don't think it necessarily means that it's faster in functional programming languages, because to give you this convenience to be able to specify it in just a few lines, functional programming languages have a larger body of things going on below. And whether or not that's faster depends on a lot of things. In particular for sorting, which is generally an easy problem. It's fast in almost no matter what you do, almost. A lot of small things matter, and one of these things is how you access memory. And functional programming is not always the smartest way to control that. They are sometimes a bit wasteful on the low-level side of things. But I'm not saying anything against Haskell. They also often have very clever optimizations that they can do. I think the true answer is you have to do a running time experiment and find out. So you're very welcome to do this and report back on the results. I'm always interested in what comes out of these things. So if you do implement it in a procedural language, this is the partitioning code that you should use. The Haskell-based representation is likely slower than this one. Like for merge sort, we can use the partitioning procedure to write a recursive sorting method, and that's then Quicksort. So again, Quicksort is given a range that we're sorting in this array, and initially it's just 1 through n, the entire thing. If the range that we're given is actually empty or just a single element, we don't do anything. Otherwise, we choose a pivot, and some comments on that in a second. After we've done that, we call the partitioning function, and then we recurse on the left and right side. Right, this is just the range to the left of the pivot position and to the right. Okay, the choice of the pivot turns out to be very important. We'll come back to that. If you take any fixed position like the first one, that's a bad idea because you can get worst case inputs very easily and they might not be infrequent. A random position is much, much better than that. It's a very sensible choice. What practitioners usually prefer is use something that makes a worst case very unlikely, but still avoid randomness for some reason. So for example, you can take 3 elements, sort them, and take the middle of those 3. That at least guarantees you that it's not the smallest and not the largest in the array that you get as pivot, but something closer to the median. Ideally, you want to choose 3 random elements and do this. Then you get the most reliable results. Now, I think this is an easy question for most of you, but I want to ask it anyways. What's the worst case running time of Quicksort? So this is important, of course. Remember for merge sort, it was true that the average case and the worst case is essentially the same, exactly the same in our cost measure of element visits. For Quicksort, as you may know, this is not the case, and that's definitely an important piece of knowledge that you should have. Let's see if I can jump over the results slide, and let's not do this. Okay. Let's give you 1 more second. I'm trying to get at least 25 or so before I close it. We've had up to 37 votes in today's session, so there must be some more people around. Okay, there you go, 25. I said I'll show the results when we're at 25. So there's a big peak for quadratic, and that's the right answer. I tried to put a lot of different things in just to make it a little confusing for you or to show what else would be possible. But yeah, quadratic is the right answer, and we'll see in a second why. Oopsies. That's definitely not correct. Have to fix the slides. That would be nice, but not true. How comes that we have this worst case? To to understand that intuitively, I think the following connection between quicksort and binary search trees that we've just covered yesterday and today and earlier today, a connection between those two is very insightful. So let's have a look at that. That might be one of the things that you haven't seen in previous classes. So everybody wake up again. Let's see how a simple quicksort would work when sorting this array of numbers. We would pick a pivot. Let's say we take the first one here for simplicity. Then we partition the lists. We just keep all the smaller elements on the left, and we put the big elements to the right. And well, I can put the pivot then between those two parts. That's how one partitioning step looked like. And I keep these boxes around the ranges that we still have to sort, so that this becomes a bit more easier to see. We do another round of partitioning, pick a pivot, partition into two parts, put the pivot in between. You know how this goes. We do the same thing for that one. And well, you keep going, right? And ultimately, every single element is just chosen as a pivot of itself, and there's nothing really to partition. But let's add that to the picture. What I added here now is the recursive call tree. There was one recursive call where 7 was chosen as pivot. And that split, that was actually the call when this was the array, and it split the list into two parts, this small segment on the right and this bigger segment on the left. And that means the recursive call where 7 was the pivot has two child recursive calls and two child trees. The one to the right with, well, this one where the pivot was 9, and on the left where the pivot was 4. So you just connect recursive calls with this parent-child relationship, and you get this tree. Okay, so far so good. Let's take the same list. These are the same numbers in the same order, right? And insert them into a binary search tree. A standard one, not the balanced one. Just one like I've shown you insert yesterday. We start with the 7. That's the first element that becomes the root, and it stays there. Then we insert the 4. 4 is smaller than 7, so it has to be the left child of 7. Next is the 2. It's smaller than 7, so we walk down here. 2 is smaller than 4, so we walk down here. Then we find a null pointer and insert it. You remember how this goes. So let me speed up a bit with the other elements. And if you just do this, insert the elements one after each other, you notice you get this binary search tree. And that looks very much alike this recursive, this recursion tree on the left. And that's no coincidence. This is what always happens. The recursion tree in Quicksort is exactly the same as this binary search tree that you get from inserting. If you pick pivots differently than in this nice simple version of Quicksort, you get the result looks slightly different, but it's still essentially true. The same result is still essentially true. So we can treat recursion trees of Quicksort like binary search trees built from just this sequence of numbers. And the connection is very one-to-one. If you look at the comparisons that you do in Quicksort, these are exactly the comparisons that you do to build this binary search tree. Now let's maybe illustrate this point one more time, because that's it's kind of clear, but maybe not so obvious at first if you see this the first time. Let's take the number 2. How does 2 find its position in the final sorted list in Quicksort? In the first round, 2 is compared to 7 and is found smaller. In the second round, 2 is compared to 4 and is found smaller. And then 2 is the pivot, so it's stuck there. So 2 participated in 2 comparisons. It was compared with 7 and it was compared with 4. Now let's look how you inserted 2 into this binary search tree. You compared with 7 at the time and found it was smaller. You compared with 4 at the time and found it was smaller, and then you inserted it here because this part was empty at the time, remember. So you do exactly the same comparisons, and you can even look at the final tree and look at the number of comparisons you need to search the two. If I search for the two, I do the same step. I traverse this. The only thing at the end, I compare with this element, and you can argue you do an extra comparison to decide that you have to stop here. But this is really a key observation here. So you can analyze and understand this complicated object Quicksort, which modifies the array over time. You can understand it using a static object, namely a fixed binary search tree that's just built from randomly inserting the elements. And well, we've already talked about how search trees look like. So you've seen this picture hand-drawn last time. A binary search tree can look like this, and then it has height n. And that also translates into a very bad case for Quicksort. You can work this out. Effectively, it's at each element you have to pay the size of the subtree, because that's how many comparisons this one participates in. And if you sum this up, you get a quadratic number, and that's your worst case for Quicksort as well. For binary search trees, we were stuck at this point with either going to a balanced binary search tree or saying, hopefully the input is not too bad. Hopefully the user is nice and does not insert elements in sorted order. Now here we have an additional option. We can explicitly randomize. By choosing a random pivot in each step, we explicitly force to have the good average case instead of whatever the terrible worst case would have been. Remember that the elements in this tree, they're chosen as the pivot in this step. So we can, by randomly choosing the pivot, we can force Quicksort to always have the good average case in expectation, and only with a very small probability we get something different. And we can do this by just randomly shuffling the input before we sort. That might sound a bit absurd or crazy. Why, if you try to bring order into a file, the best thing to do is to first completely destroy any existing order and randomly shuffle it. But yes, this is sensible. This is the right thing to do for Quicksort. That's exactly how you get the most reliable results in Quicksort, the most reliable performance. All right. I have one more slide with some results on this, but without going into much detail on this, you can work out a similar recurrence for the number of element visits for Quicksort, but I will spare you the details because the calculations are a bit longer, and I think this is a bit off the point to do that in more detail, but you can do this. And then you find the result is this, which well, this is a constant that you can approximate. It's 1.39. And remember, we had for merge sort a similar result, but it was 2n log base 2 of n. So in a sense, Quicksort brought this factor 2 down to a factor of 1.39. It's only an improvement by a constant factor, but it's a fairly significant one. And this is also what people find in practice. If you implement Quicksort properly with the randomization and with taking care of the low-level details, it's usually a good deal faster than merge sort, easily 50% faster. And that's roughly reflected in these numbers as well. You can do much more mathematical analysis on Quicksort. For example, you can prove that it's very unlikely to be much worse than this expected case. So this is the typical performance, but if you randomize, you sometimes get worse performance. But you can prove some things like this. The probability that cost is, well, roughly whatever it is, 7 times more than the expected cost is going to 0 if you make the input smaller, like this, almost like a cubic per, or at least it goes very quickly to 0. Let's leave it at that. So you can prove that the costs are concentrated around their mean. You usually get this not just in expectation, but with very high probability. And the intuition behind this is to not get something good, you have to be constantly unlucky by repeatedly choosing a really bad pivot, and that's unlikely to happen. Okay, so so much for the analysis part. This is the last slide is basically just for your interest. To wrap up the discussion of Quicksort, it's the appropriately for its name, it's the fastest general purpose sorting method in practice, and all programming libraries I know of have a Quicksort implementation. There's a particularly interesting story behind the implementation for the Java runtime library. A story that I told in the Welcome Week talk in the last fall. If you're interested to see this, I can send you a link. But you don't need to know this for our module. It has the same performance like merge sort in the average case, or as I just commented lengthily with high probability and all that if you randomize. And another good thing that merge sort couldn't do is it works in place. It doesn't need really any extra space apart from the recursion call stack. But that's very, very little compared to the large buffer area that merge sort needed. Like merge sort, memory accesses are sequential, so you don't get into trouble with caches. What's bad about Quicksort is this annoyingly slow worst case, but for practical purposes, it's largely irrelevant. If you do the proper randomization, it's probably more likely that a sun flare destroys your computer than that Quicksort really gives you bad performance. It is not a stable sorting method. That is the big downside also for practical applications, for some applications where this is relevant. It's not clear how to fix this and keep the other good properties, whereas merge sort was stable. So the usual choice in practice is if you need a stable sorting method, go for merge sort. If not, take Quicksort because it's faster. And this is another fundamental open problem in sorting. Find a simple algorithm that is fast in practice, sorts stably, and is in place, works in place. If you leave out any of the three, there are solutions known, but combining all three, no one has really convincingly done so far.